Hello again, everybody. All right, this week we're talking about duality in the simplex method. Now, I'm going to fully admit that this topic is a bit more advanced than the previous one, not because the calculations are harder, but just because duality in and of itself is not something that we generally address in a math class, right? You've probably never heard of duality before. And so part of what we're talking about at the beginning of the class is just what is duality? And then we can apply it to the simplex method case. Well, if we want to see duality in the simplex method, then we need to figure out what duality is in the first place. All right, so duality is how related problems are linked together. I've given an example here, which is sort of the generic example. Imagine I'm taking some function, f of x, and we don't need to know what a function is at this point in the class, but I've drawn its graph here, right? You can see its y value go up and go down, right? And what I've seen is that if I want to minimize this y value, if I follow along this curve until I find the minimum y value, I might call that big M, the minimum value. That is a dual problem to maximizing the negative y value, right? And it's kind of weird to think about. Turn that entire picture upside down, right? So whereas it was going up, now it's going down. And instead of bouncing and reflecting above the x-axis, now it's bouncing and reflecting below the x-axis. So I've taken the same picture and I've turned it upside down. The point here is that whatever x value minimizes this y variable, the same x value will maximize negative y. I'll get the same x value in both problems. The y value may be different, right? Notice how the y value was m here and negative m here. Because I multiplied times a negative number, of course, the solution would also be multiplied times a negative number. And I know that that's going to be the case, right? We're going to try to avoid that in the simplex method. If you look up duality in the simplex method in more standard textbooks, they would tell you to do it sort of a naive dual method, in which case you would have to multiply by a negative number to get back the original solution. Okay? The dual method we're going to look at today is totally different from that, but using the same intuitions, hopefully in a way that avoids us having to do so many intellectual backflips, but the new steps that we'll take are hopefully more approachable. And they will certainly work in more edge cases. I don't want to use the same duality method that is in the textbook, for example, because it only works in one specific minimization case. And because I can't guarantee that same one specific minimization case is going to always be true, I don't want to teach you a method which only works some of the time. I would rather teach you how to understand these problems when you see them happening in many different cases. So we have this idea of duality where we have two problems that are related, right? And we know how their solutions are related. Let's see if we can do the same thing in the simplex method to see how that changes the simplex method. I will give you a warning going into this. If you were to search Google for the dual simplex method, you are likely to find something very different from what we're going to be discussing today. Even if you click on the show answer button in My Open Math, the steps they show are for the textbook standard dual simplex method, which will not look the same as what we're doing today. Right? So please don't get confused with the show answer, but I can't turn the show answer buttons in the homework off. We'll get the same answers in the end, and I'll show you how to tell the differences between the two when we get down to that point. But just know going in that we are going out on a ledge a little bit here, right? By not following these textbook standard dual simplex method, we are having to take a little bit more responsibility to understand what we are doing instead. So let's remind ourselves how we looked at a standard simplex matrix. I'm going to just make up some numbers here. If I remember correctly, in a standard simplex matrix, this one has two x variables, two s variables, and an objective, a z value variable. This thing, because it would have three rows, the bottom row would always have its pivot here. Right? Z is always the pivot in the bottom row. And the top two rows would have their pivots somewhere else, right? I'll choose kind of at random here. Right? There were three rows and three pivots. Right? These represented the basic variables. If you remember from our last week's discussion, these are our basic variables. And you could read the values of these basic variables at the end of each row. Let's say this was 10, this was 5, and this was 9. So just by knowing this much, I could say that x1 equals 5, s1 equals 9, and z was equal to 10 at this solution. All the others, the non-basic variables, were equal to 0. And their columns could have been all kinds of junk in here. 9, 14, and -2. I just filled them in with random numbers. But we learned last week that that meant that all of those values were equal to 0 in my corner point. See, that would be S. Okay, there were only 2. And we said last week that we were making sure that all of these numbers on the right stayed positive, because if they weren't positive, remember, then we'd have a negative number in an inequality, and that meant that that meant the left than and the less than and the greater than would be sort of backwards, and we weren't allowed to do that last week in the standard simplex method. And so we made sure that all of these right-hand side numbers stayed positive. Not the one on the bottom, though. Z was allowed to be negative, although we didn't really see that much last week. Z was allowed to be negative, but you're hardly ever going to see that. And we read this simplex matrix to say when these numbers in the bottom, we call them the indicators, were negative, that meant that Z could be improved, or Z could go up. And since we were maximizing Z, then we kept repeating the simplex method pivot steps until there were no more negative numbers, because that meant that Z could no longer go up anymore. So that's when we knew we were done, is when we ran out of negative numbers in that bottom row. This week, we want to try to turn that on its head, because we want to minimize the Z value. For minimizing the Z value, we don't want Z to go up, we want Z to go down. And so we'll see that we want positive numbers rather than negative numbers. But that's kind of getting ahead of myself. I just wanted to remind you what we were looking at in a standard simplex method. We looked at these right-hand numbers here to make sure that I was still feasible, right? Am I still in the solution region? And I looked at the bottom numbers to determine if my solution was optimal or not. Right? This particular matrix represents a non-optimal solution because Z could go up. Let's see how this changes in the dual problem. In general, every time I say the primal problem, right, you can mentally change that out for a maximized problem. And anytime I say the dual problem, you can mentally change that out for the minimized version of the problem, because these two are going to be, again, flip sides of the same coin: maximize, minimize. Right, so primal feasibility was exactly what we just saw. The right-hand side, always positive. That meant that my inequalities were going in the correct direction, and I was in the feasible region. and we looked for optimality, we looked for indicators. Those were the numbers on the bottom row. I can't spell today. And when they were all positive, that meant that we were looking at the optimal solution. Right? So that's how we determined, right, primal optimality. Right? When were we at the optimal solution? Well, let's look at the dual problem. In the dual problem, we're actually going to manually make our inequalities work the same way. We're going to have to multiply times a negative number, which is going to change all the signs. But in the end of the day, we still want to end up on the correct side of the inequality. So the dual feasibility condition is actually going to be exactly the same. And we will change the inequalities so that these will be exactly the same. So when I'm all positive here, that means that I'm inside my feasible region. And it's going to turn out when we solve these minimized problems, the first matrix we write will not be this way. Right? You remember last week whenever we did our standard primal simplex method problems, the very first matrix we wrote down was feasible, right? We started at the origin, right? All the x variables were 0, all the s variables were not, right? And so we were guaranteed that the origin was always in the feasible region. So we never really had to worry about feasibility when it came to the primal problem. We were more concerned about optimality. When are we done? When are we at the optimal solution? In the dual problem, it's kind of the opposite. We're going to start out better than optimal, but not feasible. And we're going to have to pivot back towards that feasibility instead of the other way around. And for dual optimality, because we're looking to minimize the z value, right, we want exactly the opposite. Where positive numbers meant that the only place z could go was down, right, and negative numbers meant that z could go up, we actually don't want z to go up. In the dual problem, we want z to go down as far as possible. And so our dual problem will be optimal when all the indicators are all negative. Okay. That means that whichever way we move from the current position, z will always go up. And that tells us we're at the minimum value. So in reality, this is really the main difference between the two. It's how we interpret optimality. So if we go out of our way to make sure that our problems are interpreted the same way, going into the matrix, then we should be able to use 90% of the intuitions that we had in our primal simplex problems in our dual simplex problems. So a dual simplex matrix might look like this. It might have negative numbers on this side. Z would always still have its pivot. And the other two will be somewhere else. I'm just randomly making up numbers here. And so if I saw this matrix, if I look at it, right, this matrix is optimal, right? It's dual optimal, for example, because all the indicators are negative in the bottom row. So this matrix is dual optimal, but not feasible. So this is not the solution I can box in and type it into my open math as the minimum value of z. Because yes, this is optimal, but is it really, it's not a valid solution. Just because it's optimal, right, just because I can't go anywhere but up from here, doesn't mean I'm allowed to type that in as my answer. This doesn't meet the criteria of all of those inequalities that we work so hard to write. So in the dual simplex method problem, we will usually begin at a position which is optimal, but not feasible, right? And we'll actually work towards getting back to feasibility while we maintain the optimality. So let's get down to the nuts and bolts of how this is going to work. A dual simplex method problem will look something like this. It will tell you to minimize a z-value. A lot of times in the textbook, they'll use y values when they're talking minimization and x values when they're talking maximization. I don't think there's a good reason to do the difference. Like the textbook will do y values for minimization and x values for maximization. You can swap them out, you can change them, you can keep the x's, you can stick with the y's. It's okay either way, right? And of course, you will have a system. And usually, this week anyway, these systems will only be greater than or equal to constraints, which is exactly backwards from my primal simplex method last week, where they had to be less than or equal to. I'm just making up numbers here again. And here, all of these values need to be greater than 0. That one is going to pretty much stick around with us. So this is what a dual simplex method problem will generally look like. It'll still have inequalities. They'll usually be greater thans instead of less thans. Next week, we'll mix them up with greater thans and less thans mixed together. Maybe even throw in an equal sign if we're feeling feisty. But this week, we're going to try to stick to the greater thans and only the greater than. They're much easier to work with. We don't have to memorize any special rules of how to handle them. Your minimization is still an objective function. And we've got our reality constraints. So to put these greater than or equal to constraints into my simplex matrix, because remember, the simplex matrix only understands the less than or equal to constraints, I'm going to need to go out of my way to multiply times a negative number. Multiplying times a negative number not only changes the signs of everything in that inequality, but it also changes the sign of the less than to a greater than, or vice versa. So the first thing I would do is every time I see a greater than inequality, I would change it to a less than or equal to inequality by multiplying everything in that inequality times -1. You see how the x1, the x2, and the 15, they all changed signs because I multiplied everything in that inequality times -1. I'll do the same thing for the second inequality, but you see I changed a negative to a positive here. And a negative, excuse me, -20. That third one never changes. That's still a reality constraint, so you won't change that third one. This is the system of inequalities I'll put in my simplex matrix now. And I'll add the slack variables to it. And so the first inequality would be -1x1 minus 1x2 plus s1 is less than or equal to -15. That kind of comes straight out of last week's book, right? I'll add the slack variable and I'll just put it into the simplex matrix. Same thing for the second inequality, -3x1 plus 1x2, that's a positive number. Add a second slack variable, which can be different from the first, is less than or equal to -20. And I'll move all of my variables to the left side of this equation to make my objective function. Right now, that would be equal to 0. And so that should feel very familiar from last week, because that's exactly the same as how we did it last week. The only thing which is different now is that I multiplied times that -1 to make the greater thans into a less than. So right now, that's the only thing which is different between the two methods. This is not really something that I do, but it's just something that I look for. If you notice, we said that the dual problem was optimal when all of the indicators in the bottom row were negative, right? Not counting that special 1 pivot in the Z column. I see 2 indicators in the bottom row, -1 and -1 in the first 2 columns, and then the special 1 pivot in the Z column. So this matrix represents a optimal solution, but one that's not feasible. Right? We look at for feasibility in that last column across the bar. And because there are negative numbers there, we are not feasible. Right? So we're optimal, but not feasible. That's going to be a pretty standard beginning place for the dual simplex method. So our goal is to pivot towards feasibility. Right? And if I'm doing a pivot operation, just like last week, I need to tell you what's the entering variable, what's the exiting variable, and how do I determine that, right? To get as closest to the optimal solution, or in this case, get closer to the feasible region while still maintaining the optimal solution. So before, right, we looked at the bottom row, we looked at the numbers in the indicator row, and we said, okay, we'll pick the biggest one, because that tells us, right, how much Z could go up from there. But now I want to get back to feasibility. That is, I want these numbers, I want these numbers to be positive, not the numbers on the bottom row to be positive anymore. I want these numbers to be positive. And so if I want to get back to feasibility, then I choose the one, right, which is most negative. Okay, that feels very much like last week, only now I'm doing it over on the right side rather than on the bottom. So I pick the number which is most negative, and that tells me how far I am away from feasibility. And I could correct by more if I choose the second row. So just like last week, I picked the most negative number here. And what that means is the entering variable here, or excuse me, the exiting variable is S2. You see how S2 is the pivot in the second row? I want this one to go to somewhere else in the second row. That means that S2 is going to be the exiting variable here. Well, to help me decide, I need to form some ratios. Well, the ratios used to be the right side number divided by the numbers in the middle. But do you see how everything is backwards now? So now my ratios are going to be the bottom number divided by the number in the middle in the second row. This ratio is -1. This ratio is +1/3. So just like before, I'll form my ratios and I'll pick the smallest one. Right? It has to be positive. Right? So that means this right here, this number, -3, that's where I want my new pivot to go. And if that's where my new pivot should go, I'll write down that we want the smallest positive. So we want the smallest positive and the largest negative. Smallest positive means that my entering is x1. So x1 is my entering variable. S2 is my exiting variable. Right? And then I would go to the matrix tool. Right? I would do my Gauss-Jordan steps. If I were doing this by hand, and the first thing I would do is divide all the numbers in the second row divided by -3. That would give me some fractions, yes, but we learned last week that we can't really shortcut the Gauss-Jordan the same way we could on exam 2 was because if you try to do shortcut Gauss-Jordan, you'll mess up all the other pivot special ones that need to be in their specific positions. And we're not allowed to do that in the simplex method. So we're going to have to deal with the fractions. Then I would multiply 1 times second row plus the first row to clear a 0 there. 1 times the second row plus the third row to make a 0 there. And then redo my determination. We'll do a full problem with all the simplex steps involved in just a minute. I just wanted this slide in this area to be, how do I know when I'm optimal? How do I know when I'm feasible? And if I'm not those things, how do I pivot? Right? Because we spent a lot of last week deciding, how do I pivot towards optimality? Right? We found the most negative, we did the ratios, we chose the smallest positive. Right? We're doing the same thing this week, but instead of pivoting towards optimality, we're already better than optimal, right? But we're not feasible. So we're pivoting towards feasibility instead of optimality, which is why everything feels backwards. We're finding the largest negative number in the last column, determining the exiting variable first, then going back to determine the entering variable with those pivot ratios. So let's do a full problem, just because I know that everyone's going to want to see a full problem fully worked out, and let's fully explain it. That way, when we're working on our homework, we'll be able to come back and reference this. I believe I pulled this one from my particular randomization for homework problem number 1. I changed my the y variables to x variables, and I think they do a random letter like F or G. I just changed it to a Z because that's the standard I like to use. So let's look. This is now a standard minimization problem, and I can change it to, change it to be how I want it to be by changing all of those greater thans into less thans, such that ST, I'll multiply everything times -1 to change this inequality from a greater than to a less than. That gives me a negative number here. It's okay. We'll fix that. Multiply times -1. -13. I still have x1, x2 have to be positive. And when I add the slack variables in there, they have to be positive too. But we don't always write the system of equations before we go to the matrix. So I'm going to need x1, x2. I have 2 inequalities, so I'll need 2 slack variables. My objective function z, and then the numbers on the right-hand side. Sometimes those are labeled RHS, sometimes those are labeled TOT, sometimes they're labeled totals, sometimes they're labeled solutions. I usually don't label them at all. Let me pull in all of the numbers from my system. Slack variable for the first inequality. Numbers. Slack variable for the second inequality. And then let me move all of those variables to the left side in my objective function. 0. Excellent. So now my matrix is ready to go. So I'm looking at this matrix, and I'm looking at the bottom row, and I'm currently optimal or better than optimal. Right? I can tell because all the numbers are negative in the bottom row. If I'm minimizing, I'm thinking about the dual problem. Right? So dual optimality is all the numbers in the bottom row are negative, except that special 1. So we're optimal. Let's look at feasibility. I'll look at the right-hand side. Oh, there's negative numbers there. That's usually going to be the case. Right? So I'm optimal, but I'm not feasible. And so I need to move back towards feasibility. Let's determine how to do that. I choose the largest negative number here. The exiting variable is S1. And then I look at the ratios. -3 divided by -2. That's 1.5. You throw that in your calculator, that's 3/2, or 1.5. -3 divided by -1, +3. So the smallest positive is this one. My entering variable is x2. I'm going to do at least the first simplex set of operations manually, just to remind you, this is how you'll have to do it. I need to see your work on your test. If for no other reason, then you need to tell me what the operations should be. I think I have, let me check. I think I have this matrix already set up. Yeah, I have this matrix already set up in the pivot tool. So let me show my operations here instead. I'll go back and add them into the, I'll go back and add them into the OneNote after I'm done with the video. So we determined that this -2 was at the intersection of the entering variable x2 and the exiting variable s1. Back to my OneNote just to verify. Yes, entering is x2, exiting is s1. So let's make this number the new pivot. That means it needs to be a special 1. That means all the other numbers in that column need to be 0. So what I'll do is I'll multiply all the numbers in this row times -1/2. I basically do take the 2, I put it on the bottom, and negative times a negative is positive, times row 1. You don't have to show this part. Remember when we were doing this by hand on exam 2? Oh, I can't type today. Right? We do kind of the little arrow row 1. You don't have to show that part in the pivot tool. It's automatic because I wrote it next to row 1. It says, okay, well, I know that's where it's going. Do these operations, please. There we go. So now I've got a special 1, right, in the position where I want. I clear my operation. I need zeros in these two positions now. So to do that, in this tool, you have to write the row you're changing first. Row 2 plus 1 times row 1. That would give me a 0 there. The tool's going to take care of all the other arithmetic for me. That's nice. Here, row 3 plus 3 times row 1. Right? 3 times row 1 is equal to 3 in that column, plus the -3 would give me a 0. So that's really nice. The tool is going to do all the other arithmetic for me. Let's do these operations, please. First, I'll change it to a fraction mode. Now let's do these operations. There we go. Clear them out. And now I have completed one pivot operation. Just to verify for myself. Right now I'm looking at the solution x1 equals 0. It's non-basic. x2 equals 7. Right, this was S1 in my OneNote. This was S2. This was Z. And this was the blank column of constants on the other side. So S1 is 0. It's non-basic. S2 is equal to -6. Z is equal to 21. And so my Z value has gone up from 0 to 21, right? Which is in the opposite direction that I want, right? I want Z to be as low as possible. But remember, I can't let Z go all the way to -infinity because at some point I'm going to bump against the edge of my feasible region. So I'm giving up, right, as little as possible to get back to that feasible region. But I'm not quite there yet. Right? Notice how there's still a negative number here. that means I'm still not in the feasible region yet. So my z value is going to have to go up a little bit, right? But I want to get back to that feasible region more than anything right now. Next week, we will work problems where when we get back to that feasible region, maybe we're not optimal yet. Then we'll have to do it forward and backwards at the same time. This week, all the problems should end by the time we get back to the feasible region. Should. Let's do it one more time. The second row, the only negative number, that represents S2. So S2 is my exiting variable. I do my ratios here. That's 3/2 divided by 1/2. Negative divided by negative is positive. So that ratio would be 3. This ratio would be negative divided by negative is positive. 3/2 divided by 3/2 is 1. This ratio would be 1. This ratio would be 3. So I choose this column, the smallest positive ratio, which tells me my new pivot should go right here. My entering variable is x1. My exiting variable is S2. That's where the pivot is that's about to be destroyed. Okay, right, remember, normally I would just be able to click this button right here, pivot on selection, but we're doing it manually because when I'm grading your test, I'm looking for you to at least write down the row operation. Yes, use this tool or any other calculator tool to do the arithmetic for you so you don't have to work with the fractions. But I need to know that you know the correct steps of the simplex method and now the dual simplex method. Okay. Let's see, I'm going to multiply the second row times -2/3. Right? That would cancel out the fraction, right? Another way to think about 1 over a number, like 1 over a fraction, is to say turn that fraction upside down. They're called the reciprocal fraction. So -2/3 times row 2. Do that operation for me, please. Excellent. By the way, if I didn't get a 1 there, I would go back and click the undo button and then fix it, right? So don't think you have to like correct, right, for a mistake. Just undo and redo it. Okay, now clear these out. I want to clear this one, so I need -1/2. Oh, sorry. You have to list the changing row first. Row 1 plus -1/2 row 2. I know I could have just written row 1 minus 1/2 times row 2. I'm just in a habit always doing plus. Cancel this one out. I need a positive 3/2 row 2. If I always put plus there, then I can always put the opposite version of the number inside the parentheses. -3/2, positive 3/2. Positive 1/2, negative 1/2. You see, if I follow those good habits, the method kind of does itself. And I have to worry less about, am I doing the right thing, and more about just keeping it straight. Do these operations for me, please. Okay, I've verified I've correctly changed the pivot here. And I've still got all the pivots, along with 2 non-basic variables. And now looking at the end, oh hey, I am now in the feasible region because all of my negative numbers in the last column are gone. So I am now dual feasible. And just because I'm feasible doesn't mean I'm optimal though. So let me go back and look at the bottom numbers here. Aha. Don't count the zeros, negative, negative. This one doesn't count because that's the special pivot one. All the numbers in the bottom row are negative, which means I'm dual optimal. I am now done with this problem. Let's see what this says. x1 equals 4. x2 equals 5. S1 is 0. S2 is 0. They're non-basic. Z is equal to 27. So the minimum value of Z is 27 at 4, 5. Whew. I know that was a lot, right? But the nice part about it is that the dual simplex method is just the same thing as the regular simplex method, but I had to just set it up correctly, right? I know I'm looking for something a little bit different because I'm looking for feasibility rather than optimality. And next week, we're going to be looking for both. We're going to be not feasible and not optimal either. And we're going to have to kind of play around with it a little bit. But for this week, all the problems should work out pretty similarly to that. Right? You'll start out optimal, you'll start out non-feasible, and you'll do these sort of almost backwards pivot operations, right, to get back to the feasible region. And by the time you get there, you should still be optimal, and you'll have your solution right there in the bottom. Right? I'll go back and take some screenshots of the pivot tool that I just worked through, because I know that you won't be able to look at that in the OneNote if you were to click on the OneNote in Blackboard like you should be. But that's an interesting example, and one from the homework too. So that's called the dual simplex method. I apologize that we're doing it a little bit differently than you might find in a standard textbook, but we know that the simplex method problems are always really tough when it comes to searching for them on Google. You probably tried searching for it on YouTube and found some crazy things from all sorts of really complicated math classes. I apologize about that. I try to simplify it as much as possible in these videos and in the homework problems so that we don't have to do that. Right? We are doing that in the sense that we're getting the same results, but I don't want to force you to memorize it and learn a bunch more math than is necessary. All those other methods rely on some pretty complicated mathematics to all line up correctly. And because we can't guarantee that, I'd rather teach you how to interpret what you're looking at rather than hope and pray that it is going to line up perfectly every time you do it, because that won't be the case next week. Anyway, have a good one. I'll see you either later this week for another example or next week for the next set of videos. Have a good one.